The standard quadratic equation represents theoretical stability. It is clean and organized, but operationally it gives us very little useful information. Looking at this standard form, the geographic data we actually need to solve the equation, the x-intercepts or roots, is entirely hidden. It also obscures the exact center of the parabola, the axis of symmetry. To expose this data, we need to convert the equation into a different structure entirely, intercept form. In this state, the variables p and q act as explicit coordinate markers for those exact intercepts. Solving a quadratic equation is the process of forcing a translation between these two structural states. To execute this translation, mathematicians rely on two distinct strategies. The first is an observational approach, finding integer symmetries, known as reverse FOIL. The second is a deterministic strategy that engineers its own symmetry, known as completing the square. Scaling mathematics to handle complex, irregular equations requires us to move from observing patterns to dictating them. To understand exactly why the deterministic method is necessary, we first have to build and then break the discovery tool. A mathematical tool's utility is defined entirely by recognizing its operational boundaries and knowing exactly when it fails. We start by looking at the raw components of intercept form, two binomials multiplied together. Expanding this structure begins by multiplying the leading terms, giving us a times c times x squared. Multiplying the outer and inner terms yields a middle sum determined by the values a times d plus b times c. Multiplying the last terms gives us the final constant, b times d. Notice that the coefficient of the leading x squared term is exactly a times c. The constant at the end of the equation is exactly b times d. If we multiply this leading coefficient by the constant term, we get a specific product, a, b, c, d. The coefficient of the middle x term is composed of those exact same four variables, arranged in the sum of ad plus bc. The coefficients in a standard form equation are the direct result of these fixed interactions between binomial terms. We can use this relationship to reverse engineer an equation. Take 5x squared minus 13x plus 6 equals 0. We apply the ABCD rule, multiplying the leading coefficient, 5, by the constant, 6. The product is 30. We break this product down by applying the prime factorization theorem, yielding the factors 2, 3, and 5. Our operational goal is to locate a combination of factors that satisfies the AD plus BC rule by summing to negative 13. The factors negative 10 and negative 3 multiply to positive 30 and add to negative 13. We deconstruct the middle term into these two discovered integers. We group the terms, factor out the greatest common denominators, and finalize the translation into intercept form. Reverse FOIL is highly effective, provided the underlying structure yields clean, discoverable integer factors. Now consider a standard form equation, like x squared plus 10x minus 24 equals 0. If we rely on discovery, we have to map out the prime factorization of negative 24, sifting through multiple combinations and signs until we find a pair that adds to positive 10. If the constant is non-integer or exceptionally large, prime factorization is reduced to trial and error. To scale past this bottleneck, we require an algorithmic upgrade that circumvents factorization entirely. Relying on mathematical intuition has a hard limit. Rigorous problem-solving requires an algorithm that forces symmetry, regardless of the starting integers. This is the blueprint of a perfect binomial square. We take our previous test equation and intentionally break it, shifting the constant to the right side of the equal sign to leave a gap on the left. We equate our middle term, 10x, to the blueprint's middle term, 2ax. We use this to solve for the required a value, isolating a as 5. Squaring that value gives us the missing constant required to complete the perfect square, 25. We inject this engineered constant into both sides of the equation to maintain mathematical balance. We then collapse the left side into its forced perfect square state. We extract the roots by taking the square root of both sides, giving us x plus 5 equals plus or minus 7, generating our final roots of 2 and negative 12. By manufacturing our own perfect square, we bypassed the limits of integer factorization and created a universally reliable operation. Placing the outputs of the two translation tools side by side reveals their distinct mechanisms. Reverse FOIL is an observational tool, requiring you to find symmetry. Completing the square is a forcing tool, requiring you to build it. Yet this tool also has a limitation. Completing the square breaks entirely if the right-hand constant becomes negative. Applying a square root to a negative number forces the equation out of the real number system. Every mathematical algorithm is restricted by the specific properties of the number set it inhabits. Completing the square successfully solved the dependency on discoverable integers. If we apply this same deterministic process, having the middle term and squaring it, to an equation containing only the variables a, b, and c, we reach a new level of abstraction. Performing these exact algebraic steps on those general variables is what allows us to derive the universal quadratic formula. Mathematics is not just a collection of solutions, it is the process of turning a complex mechanical operation into a reliable, repeatable formula.